Good morning. We are going to see the second part of Unit 1, Thermodynamics 1. In this, we are going to study the chemical equilibrium. In a chemical reaction, chemical equilibrium it is a state in which both the reactants and products are present in concentration which have no further tendency to change with time. Usually, this state results when the forward reaction proceeds at the same rate as the reverse reaction. The reaction rate of forward and backward reactions are generally not zero but equal. Thus, there is no net change in the concentration of reactant and product. Such a state is known as dynamic equilibrium. The reaction which can go in forward as well as in backward direction, we know that it is known as reversible reaction. We know many of the reversible reaction. Now, if we start with A and B in a closed vessel, the forward reaction proceeds to form C and D. As concentration of A and B decrease, those of concentration of C and D increase continuously. As a result, the rate of forward reaction also decreases and the rate of backward reaction increases. Ultimately, the rate of two opposite reactions are equal and the system attains the state of equilibrium. Thus, the state of a reversible reaction in which the concentration of the reactant and product do not change is known as chemical equilibrium. What are the various characteristics of this chemical equilibrium? Some of the important characteristics of chemical equilibrium are as follows. At equilibrium, the concentration of each of the reactant and product becomes constant. At equilibrium, rate of forward and rate of backward reaction, they both become equals. Hence, the equilibrium is dynamic in nature. A chemical equilibrium can be established only if none of the product is allowed to escape out. If it escapes, then the reaction can go in the third direction. Chemical equilibrium can be attained from either direction, that is from the direction of reactant as well as from the direction of products. A catalyst does not alter the state of equilibrium. Now, we know the last law of mass action. Guldberg and Wag, the two scientists, chemists, in 1864, they put forward a law concerning the dependence of rate of reaction on the concentration of the reactant. This is known as law of mass action. It states as the rate of chemical reaction is proportional to the active masses of the reactants. The term active masses, it is used in the above statement. It implies activity, which we have seen in the previous talk, for the sake of simplicity, which may be taken as molar concentration. Now consider this reaction AB in equilibrium with CD. We know that R1 proportional to AB or some constant and R2 proportional to CD, again equal to some constant, removing the proportionality sign. Where this K1, K2 proportionality constant, rate constant of the reaction, rate constant of the backward reaction. And when we say a system at dynamic equilibrium, if a dynamic equilibrium is attained, then the rate of forward reaction becomes equal to the rate of backward reaction. R1 will equal to R2 and we call it as an equilibrium state. Now, we will see the thermodynamic treatment of this chemical equilibrium. Every chemical reaction, it has a change in free energy delta G, which we are dealing previously also, which is given by Van 't Hoff reaction isotherm. Suppose this is a reaction AB giving Lm. These are the number of moles. Now, the free energy of the reactant and the products are given in terms of chemical potential. We know this, G. Moles, we have to consider that we have seen in the second talk that it is not just the combination of A and B. Number of moles should also be considered. So, G of reactant will be addition of chemical potential. G of product, addition of the chemical potential of the products. Now, when we have to deal with the change in free energy, we have to see the G of product minus G of reactant. We reach to this. The chemical potential for any substance is given as mu is equal to mu 0 plus RT ln A, which we have studied in the previous series, where what is mu 0? It is a standard chemical potential, and A we call it as a activity of the substance. So this we write down for mu A, mu B, mu L, mu M like this. A times mu A, B times mu B, L times mu L, M times mu M. So putting all these values in the expression of delta G, this one, we will get this. Delta G is equal to this plus this product minus this plus this reactant. Okay, so combining the terms, we get this expression. Delta G is equal to this one. Now, what is this? In this, we are getting this activity of product, activity of reactant. What is this? Nothing but the concentration. That means equilibrium constant K. Concentration of product upon concentration of reactant, equilibrium, we take it as equilibrium. So this is nothing but activity, equilibrium constant K. So we can replace this by K, and we can write down this delta G is equal to delta G 0 plus RT ln this K. Now as we are saying that it is a equilibrium condition, so that means this delta G must be equal to 0. So if it is 0, then delta G0 will be equal to minus RT ln K. The simple expression that delta G0 is equal to minus RT ln K, this is known as Van't Hoff reaction isotherm. This is known as Van't Hoff reaction isotherm. Now, what are the basic assumptions of this Van't Hoff equation? The reacting system of the chemical reaction, it behaves ideally. First. Second, delta H has taken independent of the temperature for small range of temperature. Due to the assumption involved, delta H, delta U, they do not produce the precise values of these reactions. As delta G is independent of the pressure, for ideal system, we can say that delta H is also independent on the pressure. And that's why delta G0 is equal to minus RT ln K. It may be used to calculate the change in free energy delta G0 in the standard state also. Delta G0 for standard state and vice versa. The sign of delta G0, it will indicate the three possibilities. If delta G0 is negative, log K. If delta G0 is negative, to satisfy this equation, the log K must be positive. That means the reaction proceeds spontaneously in the forward direction. If delta G0 is positive, log K must be negative. Means K is less than 1. That means the reaction is reversible. And the reverse reaction will be spontaneous. But if delta G0 is 0, log K will be 0. Means K is 1. Means at this step, the reaction is in equilibrium. So we can find out the value of delta G0 and we can say that whether the reaction is moving in a forward direction or backward direction, or it is in a equilibrium state. Depending on this equation, we can solve some numericals. The equation is this one. Unknown quantities are delta G, T, Kp. Two quantities are given and you have to find out the third quantity simply. Now we will see what is this Kp, Kc, Kx, Kn. There are some relations between them. What is this Kp? We have just seen equilibrium constant. In terms of partial pressure, we call it as Kp. If it is in terms of concentration, equilibrium constant, we are talking about equilibrium constant only. But when we are talking in terms of pressure, we call it as Kp. Concentration, we call it as Kc. When it is in terms of mole fraction, we call it as Kx. And if it is in terms of moles, we call it as Kn. Now, the law of chemical equilibrium and equilibrium constant. Consider this reaction A, B, C, D. A, B, C, D, these are numerical quotients. and the reactants are AB, capital AB, products are capital CD. Now according to law of mass action, we know that rate of forward reaction R1 proportional to concentration of AB or equal to some constant. Same for the backward, and at equilibrium we have seen that R1 is equal to R2. That means these two terms are equal. Or if we take the ratio, we come to this. As this is the ratio of concentration, we will say that it is Kc, equilibrium constant Kc. Now, for gaseous reaction, it is more convenient to use partial pressure instead of concentration. So we write P in terms P, partial pressure. So that is Kp. We will see the relation between all these. We know that Kc, just we have derived this, Kc is equal to concentration of C, C, D, D. This expression we have derived. If the reactant and products are gaseous, then the concentration term is replaced by the partial pressure term. Like this, P is equal to concentration into RT. So we can put all these terms CART, CBRT, CCRT, CDRT in this expression. Again, we separate this concentration term and we see the power of RT is C plus D minus A plus B. What is this C plus D? Number of moles of product, number of moles of reactant. Number of moles of product minus number of moles of reactant, that is delta N. And this is Kc. So we get Kp is equal to Kc RT to the power delta N. Now we can say that delta N, if it is 0, then power is 0. That means it is 1. That means Kp is equal to Kc. Means when the number of moles in reactant and products are not changing, we can take the same value of Kp and Kc. Now we will see the relation between Kp and Kn. We have derived this expression just now. Now we have to convert this P into N now. What is the relation which indicates the equation between P and N? That is PV is equal to nRT. So we will write down for Pa, Pb, Pc, Pd and put these values in this expression. We get these terms. Again, separating the terms, we get some number of moles, RT to the power V, some power. So RT upon V, what is this again? Delta N. That means, and this is what? Kn. So Kp is equal to Kn RT by V to the power delta N. RT by V is P. So we can say that Kp is equal to Kn into P to the power delta N. Now the relation between Kp and Kx. Again, Kp is this. Now what is Kx? Kx, x, P is equal to, this P is equal to total pressure into this X, mole fraction. We know this, P dash is equal to P into X. So putting this P dash, B, P dash A as Px of B and Px of A, we reach to sum this mole fraction term and again pressure term. Power is B minus A. B minus A means again delta N. That means, or if we take this as Kx, then it will be A minus B. We can call it as minus delta N, whatever. Now about the units of equilibrium constant. You can easily take any reaction like this. You can take the terms, product on the upper side, reactant on the lower side, and you can find out the units. Now the magnitude of equilibrium constant. A large magnitude of equilibrium constant indicates that at equilibrium the concentration or partial pressure of product are very high and the reaction goes nearly to the completion. A small magnitude likewise indicates that the amount of products are very small and practically very little or no reaction occurs. Intermediate values, that is, indicates that the comparable concentration is of reactant and the products at equilibrium. Now at equilibrium, the reaction quotient becomes equal to the equilibrium constant. Means this reaction quotient becomes Kc. And if it is in terms of pressure, it becomes Kp. While equilibrium constants have definite characteristic value at a specified temperature, the reaction quotient would change with the process of reaction. Initially, if there is no product, so numerator will be 0 and this quotient will be 0, Qp will be 0. That means only reactants are present. As the reaction proceeds in forward direction, their value will increase but would be less than the equilibrium constant, means such situation will happen. That means reaction is occurring in the forward direction. If we start a reaction from the product side, that is taking C and D, now the denominator would be 0 initially and the reaction quotient would be infinity. Means only products are present. As the backward reaction occurs, A and B, that is reactants of the forward reaction, they would be formed. And it will gradually decrease the value of reaction quotient and the equilibrium will be reached. So throughout the process, we observe this. Means reaction occurs in forward direction. The reaction quotient is very handy tool. It can predict whether a given mixture of reactant and product would be at equilibrium or not. If not, in which direction the reaction would proceed in order to attain the equilibrium. Now, we will see Vent of equation for the temperature dependence, or we call it as a Vent of reaction isochron. Now we have derived delta G0 is equal to minus RT ln K. When we differentiate it with respect to temperature at constant pressure, we will get del by del T of these terms. This term and this term. Multiplying throughout by T. Substituting the values, all are the mathematical step which we can see from the notes in detail. And we also know we want to find out this quantity which we are derived from Gibbs-Helmholtz equation, that is d by dt of ln Kp. We reach to delta H0 upon RT square. So this equation is known as Vent of equation. Delta H0 is the enthalpy change for the reaction at constant pressure when the reactant as well as products are in their standard state. Now, it is well known from the experiment that the enthalpy change does not vary appreciably with the change in partial pressure. So Vent of equation may take the form that is at 2 Kp, the form will be like this at 2 temperature. So knowing the values of equilibrium constant at a temperature, it is possible to calculate the equilibrium constant at another temperature, provided that delta H is known. Alternatively, if equilibrium constant at 2 temperature is known, we can find out the value of delta H. So what is the significance or use of this equation? We have 5 quantities: Kp at one temperature, Kp at another temperature, delta H, and at 2 temperatures. 5 quantities. If any 4 is known, we can predict the remaining property. So here in this we have seen the chemical equilibrium, which is defined as the state of reversible reaction when the two opposing reactions occur at the same rate and the concentration of reactant and product do not change with time. A reaction which can go in the forward and backward direction simultaneously is called as reversible reaction. Chemical equilibrium is dynamic equilibrium. And the law of mass action states that the rate of chemical reaction is proportional to the active masses of the reactants. And we have seen the different relations between Kp, Kc, Kx. Now, in the exam, if various reactions are given, you should be in a position to write down the first equation for Kp, and then putting the suitable values, you can find out whatever is asked. Same, you can find out Kp, Kc, Kx, and we have delta G is equal to minus 2.303 RT log K. We can find out the value of delta G also. And Vent of reaction isochron, it gives the temperature dependence of equilibrium constant. Means When we know the equilibrium constant at 2 temperature, we can find out the value of delta H or vice versa. For studying this unit, you have to use these books. Essentials of Physical Chemistry by Behel, then Principles of Physical Chemistry by Puri Sharma Pathania, and Physical Chemistry by Rakshit. So these books will be helpful for you in the preparing the unit. Now various numericals are also given in the unit which you can use. So we will stop here and I will ask you to come with the doubts which we will clear.